Okay, the idea behind percentage composition is that it's the percentage of elements. Percentage of elements within a substance. Okay, so we solve it using the RAM of elements within a total RFM. What is RAM and RFM? What are these acronyms? Relative atomic mass and relative formula mass for F. Okay, so RAM of elements within and then a total RFM. So let's have a look. We would have something like CO2, carbon dioxide, nice and easy. Okay, the relative formula mass of CO2 happens to be 44.01. Okay, but that's composed of two parts. It's composed of the 12.01 and the 2 times 16, the carbon and the oxygen. Okay, to work out the percentage composition, we would say, okay, what's the percentage composition of carbon? It would be the relative atomic mass of the carbons within that, so just that one carbon for this example, over the total RFM, times 100 to make it a percentage. Okay? Okay, which is what? 27.3%. Okay. And then we can do the oxygen, which would be the percentage of the O, which is equal to the 32 times 44.01 times 100, which would be equal to, what, 73.7%. Here's a question. Where did the 32 come from? Where did this number appear from? Out of nowhere. Where did this number appear from, Krishna? 2 times 16 from the oxygen over here. Right, cool, excellent. Seems fairly straightforward. Okay, cool. Let's work out the percentage composition of a number of other things. So let's do, I'll leave that one up there. Let's do H2CO3, also known as carbonic acid. Let's do calcium phosphate. And let's do aluminium nitrate. Okay, so you need to work out the percentage of each element there. Percentage of hydrogen, percentage of carbon, percentage of oxygen. Right, for this one it'd be the percentage of calcium, percentage of phosphorus, and percentage of oxygen. And then you can work out that one. All right. If you want to, you can have a go at doing these without looking at the board. I'm just going to do them on the board if you get stuck, but I would really, really recommend you try to do these without looking. All right? But you will need a data sheet to do so. There are data sheets at the front if you want to grab them. I'll leave that one up there so that you can see. That seems a bit large. Mr. Lim doesn't. The next idea is called empirical formula. Okay, so the idea is that if you have, if you know that there is two elements within a substance, like C and O, right? There can be multiple ways that you can combine C and O together. Multiple ways and multiple molecules that you can make. You can make CO, which is carbon what? Monoxide, or you can make carbon dioxide. All right? There's two ways that you can combine carbon and oxygen. Just like there's a number of ways that you can combine carbon and hydrogen. Even in the same thing, you can have CH4, or you can have C2H6, or you can have C2H4. There's multiple ways that you can combine various elements together to make different molecules. Okay? And so the first part of analyzing these things and working out what that substance is, because maybe you will know what elements are in there. You will know what elements are in there, but you don't know their arrangement. The first step is to work out what the ratio is of different atoms to different elements within the substance, right? Working out the ratio of it. So this ratio here is a 1-to-1 ratio. 1-to-1 ratio. This is a 1-to-2 ratio. Make sense? 1-to-4 ratio. This is a 1-to-3 ratio, and this is a 1-to-2 ratio. Happy with the idea that the first thing you need to do is work out the ratio of them to each other. Right? Or at least that's one of the steps. So, first of all, here's looking at this one here. Why did I write it's a 1-to-3 instead of writing it's 2-to-6 like I've done with all the others? 2 and 6 are multiples of 2, and therefore this is effectively the simplest whole number ratio. Whole number ratio. Okay? So this is the simplest whole number ratio of those particular elements to each other, right? This simplest whole number ratio is and can be expressed as the empirical formula when you write them out like so, right? So this simplest whole number ratio as an empirical formula for this one here, the CO, would be CO. Because it's a 1-to-1 ratio, it is the simplest whole number ratio. The simplest whole number ratio for CO2 would be what? CO2. It is its simplest whole number ratio already. Okay? CH4, again, would be its simplest whole number ratio. Now, how do I write down C2H6 in its simplest whole number ratio? This would be what? CH3. Excellent. And the next one in its simplest whole number ratio would be CH2. Okay? So, this here in blue is the empirical formula. This here in black is what's known as the molecular formula, which is its actual ratio. Okay? The empirical formula and the molecular formula, its actual ratio. So, the empirical formula is the simplest whole number ratio of various things. So let's go have a try at working out some empirical formulas from molecular formulas. if I write down this C2H6O2 or AlCl3 and maybe let's do C6H6. Okay, here are three substances. This is their molecular formula. Technically, the AlCl3 is not a molecular formula, but it doesn't matter. Right? But what is their empirical formula? Have a think. Write down what you think will be their empirical formulas. Don't look at the board once you've written down the answers, or once you've written down the questions. Don't look at the board until you want to check. Okay. So, give you another 30 seconds. Okay, so those are your three empirical formulas from the molecular formulas that you were given. Okay, so some task will be identify what is the empirical formula of this substance, and you just work out the simplest whole number ratio. Okay. Now, we can do this experimentally as well, because, let's have a look. The empirical formula is the simplest whole number ratio, and the simplest whole number ratio effectively says that, okay, if I have a CO2, if I have 100 atoms of carbon, how many atoms of oxygen will I have? 200. Does that make sense? Nice and easy. Okay? If I have 1,500 atoms of carbon, how many atoms of oxygen will I have? 3,000. Nice and easy. All right? Now remember, moles is just a word to describe a number. So if I have 1.2 moles of carbon, how many moles of oxygen do I have? 2.4 moles. Happy with that idea? All right, you can start off. That's what the ratio shows. So if I have 1.2 moles of carbon, I have 2.4 moles of oxygen. Okay? Now, that can translate to masses as well. Okay? 1.2 moles of carbon is 14.412 grams. And 2.4 moles of oxygen, or that O2, also that oxygen, it'd be 2.4 times 16, which would be 38.4 grams. Okay, so that is from the 2.4 times the 16, not the 32. Okay? So, I can have the mass of these two things there showing me the ratio of atoms. Okay? So, if you really to think about this as well, this CO2 as a percentage of each other was all the way back up here, 27.3% carbon and 73.7% oxygen. So 27.3, C was 27.3, O was 72.7. Happy with that idea? Right, that's what we saw before from this carbon dioxide. We could translate that to masses, because a percentage effectively says that it's going to be in 100 grams, it's going to be 27.3 grams of carbon and 72.7 grams of oxygen. Okay? So, the percentages can be turned into grams in 100 grams, because that's what a percentage describes. Okay? We could then work out the number of moles of these two things. the number of moles of carbon is equal to, for example, 27.3 over 12.01, and the number of moles of oxygen would be 72.7 over 16. Okay, so it would be like, hopefully that's right, 27.3 divided by 12.01 would be 2.27, right? And then 72.7 divided by 16 would be 4.54 moles and moles. Okay. Okay, so look up. We're happy with the idea that you can have 1.2 moles of this and 2.4 moles of this. Yeah? From starting out with atoms. We're happy that we can work out the percentage of carbon from there and then happy with them being in masses. But what I want you to do is look at what's the relationship between this and this. They're still in the ratio of 1 to 2. Right? As we expect, it should be so. Okay? So, it's still in the ratio of 1 to 2. So therefore, a percentage here can lead you to get to the ratio of the substances that you have. A percentage can lead you, if you follow the right steps, to the ratios of elements within a substance. At least the simplest whole number ratio. Can't lead you to the actual ratio yet. Okay? So, we can look at 2.27 and 4.54 and say that, oh yeah, that's a ratio of 1 to 2. But if we were to really wanting to show this, we would have to do a calculation to turn those numbers into 1 and 2. Okay? So, which is effectively saying, if we didn't have such nice numbers, could we have a way to do it so that it would help us, instead of being able to be like, oh, 13.6 and 56 point something, what's the ratio between those two numbers? And be like, oh, I don't know, something. All right? So, a way that we can do this is we divide, oops, that's not what I want. Divide by the, anyone? Divide both by the smallest number of moles. Okay? So, if we were to take this one here, and we would say, okay, carbon and oxygen, the number of moles is 2.27, and the 4.54, and I'm building a table here if you haven't worked that out. All right? Then I divide by the smallest, be 2.27 over 2.27, which is exactly what it is, and 4.54 over 2.27. And so therefore the ratio would be, this value here would be 1, this value here would be 2. Okay? So that structured table allows you to show the number of moles, you divide by the smallest, and then their ratio to each other. It's ideal because it makes everything nice and neat, and when you get to year 12, they'll be much bigger, and so you want to try and keep everything neat. All right? Especially because you're also showing what you're solving for. You don't want to just be like, oh, I'm solving for this, but then you don't say it. So it's always good to show what you're solving. Okay? So that is the steps for working out empirical formula from a percentage. Okay? You start out with the percentage, you turn them into mass in 100, and this is actually a really important step. So start off with the percentage, turn the percentage into mass, that's an important step to state. Turn the mass into number of moles, and then make a table to show the ratio between them. So let's try with the ones that we did before. Let's just confirm that they will actually do the exact same thing. So we worked out percentages of these ones here. Okay, let's do this one here, calcium here. Okay. Let's take this one here. Okay, cool. So let's do this one together, and I'll walk you through the steps. Okay. Happy with those? All right. So first of all, I say that mass, and we're going to just start off with one element. We'll start off with calcium. The mass of calcium in 100 grams is equal to 38.76 grams. You have to state this step, because without stating this step, you're turning a percentage into a moles, and that just doesn't work. So you have to say that I'm converting it into a mass, and you have to kind of annotate that it's in 100 grams. The next step would be to work out the number of moles of calcium. 38.76 divided by the molar mass of calcium, which is 40.08, which happens to be 38.76 divided by 40.08, which happens to be 0.967 mole. We're going to save that as A. Then I can do the next one. The mass of phosphorus is equal to 19.97 in 100 grams. And then I can work out the number of moles of phosphorus. 19.97 over 30.97, which will be equal to 645 maybe? 645 mole, which I'm going to save as B. And then finally, I'm going to do the mass of the oxygen, which is equal to 41.27. Then I can work out the number of moles of oxygen, 41.27 over 16, which is equal to 2.58 mole. 2.579. I'll go to 3 decimal places. And I'll save that as C. Who can see what I've done wrong in the last calculation? Who can see what I've done wrong in the last calculation? I didn't tell you that it was in 100 grams. Good. Excellent. I know. Useless, sir. God. Okay. Are we happy with those steps so far? Okay, cool. This is why we saved numbers, because we're about to do, what do we need to do next? Make a pretty little table. Calcium, phosphorus, oxygen. The first layer in the table is the number of moles, which we will just restate. Lucky for me, I'm lazy and I can restate the letters that I've saved them. Then I do what? What's the next step? What's the next step? Divide by the smallest. Which one is the smallest? 0.645, which happens to be B. So I will do A over B, B over B, which will be 1, and C over B. And that will give me the ratio, or the simplest whole number ratio, alternatively known as the empirical formula. This is why we save numbers, yeah? So, save the first number, A divided by B, A divided by B, 1.49. 9, which effectively is 1.5. And then C is C divided by B, 4. Okay. Now, I have the ratio of calciums to phosphoruses to oxygen. However, I do not have the empirical formula, because the empirical formula is defined as the simplest whole number ratio. this is not a whole number ratio yet. It is an unwhole ratio number. All right? So, how do I turn this into a whole number ratio? Any ideas? Times what? Times what by 2? Everything. Please remember you have to multiply everything when you do it. So you do multiply by 2, this becomes 3, 2, and 8. And so my empirical formula is Ca3P2O8. And if you're real clever, the P2O8, you should know that it's a PO4, bracket 2, and we go all the way back to where we started at, with the formula of calcium phosphate. Okay, so a couple of things about simplest whole number ratios and that last step here. This 1.5 is not uncommon, okay? Whenever you have something that ends in 0.5, so something, it's never going to be 0.5, but something 0.5, you times everything by 2. Because 0.5 as a fraction is 2, half. What happens if you see a 0.33? What should you times it by? Times by 3. What happens if you see a 0.67? Times it by? Times it by? 0.67 is what as a fraction? 2 over 3. So to turn it into a whole number ratio, you turn it back into times by 3. Okay? If you see a, what do you think the next one will be? 0.25 by 11? Incorrect. What's another one that you can times by 4? 0.75s. Okay? And rarely will you see 0.2s, but they do exist, and which you times it by 5. If you see a 0.167, that's a 6, I think. All right? So, but you're rarely to see those. Okay? But those are the common decimal places that you will see when you're doing these empirical formulas. All right? So let's have a go at doing the next one here. Let's do this one here. Oops, I don't want that part. Undo. I just want this part. Zoom out. Take that. Put it over where somewhere. Okay, there we go. Okay, you guys have a go at doing this one. Don't look at the board, I'll be writing up the answer, but have a go. Or if you're unsure about a step, please come and ask. But try not to look at the board. Try and remember or look at your old steps and do them again. Remember to save values on your calculators. Victoria, do you know how to save values on your calculator? No? Okay, come here and I'll show you. And here are the answers for that last one.